Well, thanks for all coming. Like Paul says, this is going to be a kind of overarching presentation of touching the topics in my thesis, and which was originally kind of a brainchild of Cam McQuaig, and it was carried to the finish line by Sandy Occhipinti, Karsten Laukamp, and Marco Fiorentini, who were my supervisors on this project. This one. Motivation for doing a distal footprint study for base mineral deposit came from this particular slide that you've probably all seen, that where all the cost of exploration is kind of exponentially growing, but no one's still finding anything. And one of the speculations why that is the case is that nowadays most of the unfound deposits are undercover, and because they are undercover, you can't actually detect them using any direct method. So exploration happens through various kind of proxies, and these proxies usually are quite specialized. So people need to actually understand a great deal of science or some sort of technical aspects, and also understand different kind of deposit styles. So there's a lot of knowledge of these in the minerals exploration field, but most of the time it kind of requires specialized skills, which kind of can lead to a fragmented view of the kind of overall how to control things and actually find things when you only specialize in a narrow aspect of things. So, and that's why perhaps we don't understand or what are we actually looking for and what kind of science. And that's why, and the aim of my PhD was to kind of provide more of a holistic view using multiple different kind of geoscience tools and in different scales that are easily accessible, and put some sense to it and make a distal footprint in 3 different scales. I'm going to talk about briefly of the crustal architecture. So Abra is situated in the Capricorn Orogen between Pilbara Craton and Yilgarn in the Edmund Basin. But I'm just going to show the kind of key elements of the architecture part of my thesis. If anyone's interested in reading my thesis, I'm happily sending it to anyone really. And but the most kind of, I'm putting most of my efforts to explain more about the deposit scale footprint and the alteration halos around the undercover base mineral deposit. And then I'm going to, and that's which is situated about 300 meters from the surface. And then a little bit about the weather mineral footprints and how to detect them directly from the surface, and then how to apply ground truth remote sensing data sets to kind of use those as an exploration tool. A little bit of summary and some accessory slides just for discussion in the end. So first thing about the architecture. Architecture can be perceived as a bit of a crustal scale mineral footprint if you take in and what the mineral systems analysis is presenting. So the carrying idea for the this kind of like lithospheric scale footprint is that there are 2 different kinds of older geological domains which are covered by another layer of either sediments or volcaniclastic rocks, and with the extensive history on these kind of fundamental basement structures, it causes enrichment of metals in these kind of terrains, and then hopefully leading to this kind of a deposit forming in case of Abra in the sediment-hosted sedimentary basin. In a kind of a 2D map view, the same scenario is that you have one domain here, one domain here, and then two different kinds of basement structures intersecting, creating kind of endowed pathway for mineral deposits to form. However, this is when it's covered by, for instance, by a sedimentary basin, as the Edmund Basin is, you wouldn't be able to detect these kind of crustal scale features by just mapping. Crustal scales, like Abra, well, the whole area where Abra is situated, the basement has a tectonic history spanning over 2 billion years before formation of Abra, and some major fault zones are in the region Cordelia Fault, which is kind of perceived as a structure between Yilgarn Craton and Glenburn terrain, and then Talga or Lions River Fault, depending who you ask, which could be a structure between Glenburn terrain and Pilbara Craton. So these are the kind of forming, kind of intersecting juncture, and these would have formed before the Abra deposit actually formed in the later Mesoproterozoic extension. In the present day map, so here are the origin parallel Talga and Lions River Fault, which is in the area where Abra is actually known as a quartzite well fault, just to add to confusion. That's perceived as the main first order fault hosting Abra deposit. And there will be the Cordelia Fault terminating these two origin parallel faults. In these total magnetic intensity grids, I'm not sure if you can see it, but these, in the area where Abra is situated and where most of the base mineral deposits shown in very, very tiny red dots, there is a kind of regional magnetic high. And north of Abra, there is a gravity high between the Quartzite Well Fault and the Talga Mount Vernon Fault. I did some, and these are kind of fitting between these major structures. I did some forward modeling, and based on that effort, it turns out that the high magnetic intensity and gravity are actually coming from the basement and not from the superficial rocks or from the actual sediments. So there is something beneath in this area that is potentially kind of causing this kind of geophysical footprint. I'll just need to look into it more. But anyway, going to the main kind of cores of the talk. So deposit scale footprint. I'm going to go through a little bit of terminology, just go briefly through weathering aspects, and then actually go to the Abra geological background, and then methods and how I identified the mineral footprint from the hyperspectral data. Sediment-hosted base mineral deposits are kind of a loosely defined territory when it comes to terminology. So depending on who you like, every author seems to prefer their own description of each deposit. Commonly used are SEDEX or plastic dominated or replacement style deposits. These deposits can form as a replacement or exhaling to the seafloor. However, because of the kind of problem with comparing apples and pears, you don't necessarily know what kind of deposit is the author talking about. If the exhalative and replacement deposits are kind of put in the same category. These SEDEX-style deposits have, or sediment-hosted basin deposits have quite a bit of common in terms of the general terrain where they form, and also the kind of characteristics that they can have with the volcanic hosted massive sulfides. However, sediment-hosted basin deposits, they tend to have more of a carbonate alteration, whereas volcanic hosted massive sulfides tend to have chlorite and white mica footprint around them. Weathering, this is a picture of from a top of Abra. There is mostly subcrop and some actual outcrop, but in situ lag is, well, is perceived, it's considered in situ, and then you have the weathered outcrop that is weathered to the depth of about 60 meters from the surface. Weathering can cause changes in mineral compositions, usually by, like, for common alteration minerals such as chlorite, which goes from smectite to kaolinite, and then polyaldered kaolinite when you're going to very weathered terrain, very weathered conditions. However, white mica or muscovite or phengite, white mica term kind of encompasses the both muscovite and phengite, is fairly resistant to weathering, and that's why I'm putting quite a lot of effort explaining about white mica and why you should care about its compositional shift and on all the wavelength stuff that might confuse me in the beginning, for sure. So, finally about Abra. It's hosted at about, well, it's situated at about 300 meters depth from the surface. The stratiform lead zinc mineralization is kind of in the interface of the Kiangi Creek Formation and the Irigaray Formation. The stringer zone hosting most of the copper and gold is within the Irigaray Formation. What was I going to say? The overlying sediments, and it actually has like chlorite, siderite alteration, but the overlying sediments were believed to cut the alteration and mineralization above the deposit. So these overlying sediments were considered much younger and kind of erasing all of the traces of the alteration and mineralization. There are a few pictures of the actual mineralization. So this is the red zone on top, the black zone where the most of the lead and zinc are, and then the stringer zone beneath. So the way I mapped the alteration is based on the high-logger data from AB62 and HY2, and then used and did validation for the mineralogy from these Reflectance Spectra data using SEM and EDS analysis, micro-XRD and optical microscopy, and then transform that, use that information to interpret the spectral data from 26 drill holes that are actually intersecting the Abra deposit. In case someone hasn't seen already these, so this is the high-logger 3 instrument, and these are the HY2 and AB62 drill core data is captured with this machine, device, technology. It captures, measures spectra every 4 millimeters, and it kind of creates a continuous scan along the drill core. It collects very near infrared, shortwave infrared, and thermal infrared spectra, and then whereas the Field Spec 3 spectrometer, which was used by Abra Mining at the time of, I don't know, 2006, when they were doing measurements. They collected spectra every meter, and this spectrometer collects very near infrared and short-wave infrared spectra. From wavelength scale, the very near infrared is good for identifying iron oxides and ferrous iron, and SWIR is good for chloride, white mica, and carbonates to some degree. Thermal is pretty good for identifying carbonate chemistry, and which I will use to calibrate the carbonate classification in the SWIR for the deposit scale. Reflectance spectra can be processed in two main ways, I suppose. One is to have a kind of reference library, which the algorithm matches the collected spectra and creates and brings out an mineralogy that matches this kind of a old spectral curve. The other way is to use scalars or filters that specific mineral-specific absorption features in the collected spectra. And how you do it is that you apply, how I did it is that I applied from a kind of a coarser scale aluminum OH feature spectra, which is the 2200, that is found in white mica and kaolinite, and also aluminum smectite, and then use another filter to specify, separate the kaolinites and white micas from this kind of aluminum OH group, and then finally separated by the wavelength position, which of the white micas are muscovite and which are phengite, which is based on Chermak's substitution on white mica chemistry. So in muscovite you have aluminum, and in phengite you have iron or magnesium and silica replacing the aluminum, which causes the spectra, the aluminum OH feature, to shift or position towards the longer wavelength. And when you apply these scalars in specific order and kind of take care that you have kind of, you apply it from coarsest to a smaller scale, you can identify 9 different mineral compositions from the SWIR spectra. And carbonates, and then when you shift it to carbonate thermal processing, carbonates have 3 peaks, and for instance this is modified after Green and Shotlock. So first peak is filtering out all spectra but carbonates, and these 2 other peaks are identifying the composition between siderite and dolomite, iron dolomite, and ankerite, which are then these compositions are based on pure library samples, and that's well, essentially what you see here is that none of these samples are actually necessarily pure. It's just a reflection of the kind of the closest possible composition, but you kind of need to name them somehow to keep sense of things. Then the thermal infrared classification for carbonates, I use that for training the shortwave infrared spectral processing, and which related to, which is based on the iron intensity in the shortwave infrared, in the very near infrared, and then the carbonate feature on the SWIR spectra, leading to somewhat reliable classification for SWIR, which is I applied for the Abra deposit spectrum. Sorry, I need to drink. So that's all about the processing. I hope I confused everyone only little. So when you are interpreting any kind of alteration mineralogy, you need to understand the actual geology in the area. So establishing kind of a comparable stratigraphic units before interpreting anything is crucial. So this is the conglomerate strata where the Abra deposit is situated. We are looking at these two drill cores here. In HY2, the conglomerate strata is completely altered to red zone. AB62, it's still fairly pristine, and the most mineralized area is actually in the Uri-Gully formation, a little bit lower than in the deposit. So what I was explaining. So what we got here is that there are some deep shelf sediments, fan delta sediments that are considered as the later marine flooding sediments, and then you have the deep shelf sediments underneath. These are mostly siliciclastic, and these are carbonaceous. So now the results. You can see the upper part of the drill core has more of a iron dolomite composition. In the conglomerate, you have more dolomite, and in the more of a mineralized part of the core, there is a lot of siderite, and in the lower part, anchorite, and this is from the thermal spectra. Whoops, getting really confusing. The SCM-EDS analysis show that there are several carbonate compositions in these intervals. So the original carbonate was dolomite, which was then replaced by iron dolomite and anchorite. And in the mineralized zone, from the SCM-EDS analysis, I was able to determine siderite, first order manganese siderite, and then later more of a sideritic composition in carbonates, and even later kind of weird combination of manganese, magnesium, iron carbonate. In the Uri-Gully formation, there's mostly detrital siderite, which seems like a primary feature and not related to alteration at all. And it has almost stoichiometric siderite composition, so it doesn't have any manganese. And then there's a later anchorite alteration, anchorite carbonate. White mica and chlorite. The interval from the conglomerate and to the mineralized interval is fairly phengitic. It's abundant in white mica. It's slightly phengitic. It has a long wavelength signature, so the white mica contains iron and magnesium and manganese. The phengitic alteration in the SCM-EDS analysis relates to very fine crystalline white mica or ceresite, which is replacing potassium feldspar. And the chlorite in the upper part of the core is magnesium rich, whereas the lower part of the core is iron rich. these chlorides seem to be a little bit different than the rest of the chlorides in the lower part of the core drill hole. Most of the chlorides in the lower part of the drill core are actually interlayered with the sphengitic white mica, and kind of even in this little grain there are several chloride crystals. And then HY2, which is more mineralized, so we should expect to see more alteration or zonation or something, some sort of trends at least. And in carbonates, you have a trend going from siderite to anchorite to iron dolomite, and you don't see any actual primary dolomite in this area. For chlorite and white mica, this is from the logged alteration chloride, and it's actually quite well coinciding with the interlayered chloride and white mica in the reflectance spectra. Most sphengitic composition is in the lower part of the core, where even the SWIR identifies carbonates in that part. Yeah, before going there. So, before going to the actual deposit and its spectra, I had to also establish some sort of lithological boundaries or reference points to interpret whether the alteration was real or it was overprint or was it something primary. Unfortunately, despite there has been a lot of studies about Abra, the kind of contact between red zone and the overlying sediments wasn't really that well described. So what I did, I relogged some of the, grouped some of these 50 lithological groups that were in the company database and matched them to create more of a robust kind of a base for the interpretation, and also check the contact for the red zone and the overlying sediments. It seems like in the northern part of the deposit, the red zone alteration actually intrudes the overlying sediments, which should be eroding the mineralisation and the alteration, which isn't the case, at least to me. And this was something that company geologists or exploration geologists on the site were telling me that that's their interpretation, and it's kind of easy to agree with them with that. And then furthermore, the red zone and black zone alteration, they are kind of parallel to the strata, whereas the underlying stringer zone is more chaotic and has a chaotic and more of a kind of a mixed composition. So they all have, and which is then Anyway, most of these veins that are intersecting the deposit that are not related, kind of a later veins, they seem to follow the kind of north dipping fault zone intersecting Abra. Anyway, that's the geological framework. That now back to the spectrum. We have there's a coarse grains quartz sandstone there, and the chloride white mica alteration is overprinting this one lithological unit, which seems to be, which implies that it's not primary feature. Furthermore, beneath the deposit, the most chloride alteration is the most intense in the center, and the siderite is kind of focused on the close to the conglomerate. The aluminum OH feature wavelength, it's indicating most phengitic composition near the northern part of the deposit, and then away from the deposit you have a shorter wavelength signature. It's, if you can, I'm not sure if you can see that these are kind of a light blue colors, which indicates that the wavelength has shifted towards the wavelength of a kaolinite, which means that they've been weathered. However, they are well enough preserved that you can identify these from the surrounding spectra, surrounding shorter wavelength white mica composition. This, yes, so based on the carbonate replacement in the overlying sediments, and then the kind of vertical zonation identified that I just identified from the high logger spectra, plus the vertical zonation of chlorite white mica and the phengitic composition preserved near the surface, it would seem that it's not a SEDEX deposit or exhalative deposit, but possibly most likely formed through replacement, and when these overlying sediments were either rapidly depositing or generally existing above. The preservation of the long wavelength signature in the white micas enables us to map that from the surface, which is kind of what I did from the regolith. So I used the field spectra to ground truth the ASTER satellite data, and then potassium use ASTER satellite data and the aluminum OH composition that you can get from it with the potassium radiometric data to map out white mica alteration. Resolution is less in the ASTER spectra, in the ASTER multispectral data. However, you can still get some sort of a vague compositional composition of a white mica, and this is the result. So here we have different lithologies going from sandstone to siltstone to dolostone. There's a long wavelength aluminum OH group composition in ASTER spectra, which is coinciding with the potassium radiometric high. When you overlay them, you see that these kind of follow the areas where the field spectrometer shows chlorite and longer wavelength white mica, indicating that you can actually use these remote sensing data sets as long as you ground truth them to map these kind of alteration footprints. However, this is kind of only, well, it works best if you have mica pore lithologies to compare them against. So, in summary, Abra lies above an anomalously dense and magnetic basement. It's possibly in the triple junction of two major basement, fundamental basement structures. It has vertical footprints of very fine crystalline chlorite phengite alteration, which is phengitic in distal and more chlorite in the proximal to the deposit. The phengitic footprint is preserved to the surface and is detectable from reflectance spectra, field data, and remote sensing data. Dolomite matrix is replaced by manganese siderite, anchorite, and iron dolomite, which is both of these the vertical zoned mineral footprint above Abra, and then the carbonate replacement implies that it's replacement deposit, not an exhalative. And these kind of footprints, I don't know if you remember, but they briefly mentioned that sediment-hosted base mineral deposits don't usually have chloride white mica alteration. They usually have carbonate footprints. Whereas the volcanic hosted massive sulfides have more of a chloride white mica footprint. Same as with the polymetallic carbonate replacement skarns and a few others. So here is, these are sediment-hosted basement deposit. Century deposit has manganese anchorite and manganese siderite alteration related to proximal to the deposit. Same is here's your chance deposit. Sullivan has muscovite, sericite, chloride, albites alteration on top of the deposit. Which is kind of odd considering that Sullivan is considered as a classic exhalative deposit. And then you have RK and VMS deposits with the proximal siderite and kind of medial anchorite, iron dolomite, and distal dolomite to calcite alteration. Another VMS deposit, New Brunswick number 12, has manganese, iron manganese chloride, which is kind of intermediate chloride composition, and phengite above the deposit, and then iron chloride in the kind of a stringer zone of the deposit. Where am I getting at? There's been recent study of Abra that its ore mineral signatures, like ore mineral chemistry, links to closer to sedimentary copper, skarn deposits, and VMS deposits than actual sediment-hosted massive sulfides. So, yeah. And I'll leave it to there. Thank you. Anyway, sorry.